All right. Hello, everyone. So it's about time to get started. Um, Homework 7 is due now. Okay, I think most of you guys have submitted your homeworks online on Moodle, and next homework will be due a week from now. Okay, it's also going to be on Moodle. I think I have that already. Now it's available right now. Okay, so that's on the next one here. So today we are going to start checking chapter um, 16, planar rigid body motions. Okay, so up to this point we have been talking about the motions of a point particle, which we actually can treat a lot of particles as point particles. Okay, but in some cases, when the motion of the object become complicated, so then we can no longer treat as a point particle. So then this is the topic we want to cover here, starting from this chapter. Okay, so we'll be doing reading quiz, and then we'll be checking um, 3 sections of this chapter, and then we'll be looking at a few examples in the form of concept quiz, attention quiz, and then we'll be looking at group problem solving if we have time. Okay, so again, let's get started with the reading quiz. All right, so reading quiz is here. All right, send your responses with the chat option to me. All right, I think I have all your responses here. We can take a quick look on the answers here. So the first one here says if a rigid body is in translation only, the velocity at points A and B on the body should be always the same. So if a body is in translational only, then every point on the body will have the same velocity at all the time. Okay, so that's what the translation is being defined. The second one, if a rigid body is rotating with a constant angular velocity about a fixed axis, the velocity vector at point P, all right, so this is also defined in the textbook, is defined as omega as a vector cross product the position vector at point P, okay? So it's omega cross RP, all right? It's not the other way around. It's not RP across omega, but it's omega cross RP, okay? dr over dt would just give you the yeah, this is the definition of the velocity from translational um, motion. Okay, so that's not C. So B and A will be the answers for the reading quizzes. Okay. All right. So any questions you guys might have? I'll pause for a few seconds before we move on. If you have questions, just unmute yourself and then talk. Okay. Okay. If not, then we are moving on, checking on the sections here. So we'll be checking on 3 sections today. 16.1. All right. So as I said, there's scenarios involved that you cannot treat an object as a particle. Then that's what we are talking about here. Okay. So in some cases, if there's rotational involved, then that's the situation. Okay. That's the easiest scenario or the common scenario here. Okay. Um, so, for example, when you have rotations, you can think about like gears, links, or cams, etc. Okay. So, but we still can have the object as a rigid body. Okay. So that's all we are doing. So basically, for rigid bodies, there are 3 types of motions for rigid body. The first type is called translational motion. Okay, so and then on the first type for translational motion, you could have 2 types. Okay, so that's the one up here. So you could have rectilinear translation. So this is going to be parallel. So you are going to draw a line from any 2 points within the body. Okay, so this line during the motion is going to be from one point to any other point. It's going to be parallel to the original. Okay, so this line is perpendicular or parallel to it. Okay, so at any given moment, if you track the positions of these lines at different time instance, then they are all parallel to each other. So this is the translational motion. And then if you connect the to the same points during its, or you trace the movement of the same point, it's going to be a line. Okay, it's a straight line. Then this is a rectilinear translation. If the line curves, okay, but still, if you connect 2 dots in the body at any given moment, you look at this line, it's going to be parallel to the line at some point later. And this is also translation motion, but if you connect the same or trace the same point during the motion, it curves, then it's called curvilinear translation. Okay, but both are translation motion. All right. So in both scenarios, any point in the body will have the same velocity and acceleration, etc. Okay, so similar here, although it curved, but at any given moment, these 2 points will have the same velocity and acceleration. Okay, The second type of motion is called rotation about a fixed axis. Okay, so if you have an axis going through a body, it doesn't necessarily have to be going through the body. It could be outside the body. Okay, in that case, so any points from the rigid body here, then we'll have a circular motion. Okay, it's going to be moved about an axis, either going through the body or outside of the body. Doesn't really matter. Okay, as long as it's a fixed axis. Okay. So then in that case, this rigid body is having rotational motion, all right? Now, in general, you could have combination of rotational motion and translational motion, okay? So if you combine 1 and 2, then you will have generally have a general plane motion. So this guy, okay, you can see it could have translational, go from one point to another point. It could also rotate about a certain axis, okay, going through the body here. So that's the general plane motion, okay? All right, so those are 3 types of planar rigid body motion. So more details. The first type, translation. Okay, so as I think we briefly explained in the previous slides. Okay, so in this case, if every line segment on the body remains parallel to its original direction during the motion, so that means you take any 2 points, you connect them, then this line during the motion will be parallel to each other. Okay, so and then when all the points move along a straight line. So if you look at a particular point, it's going to be moving along a straight line. It's rectilinear translation, okay? If the line curves, then it's going to be called curvilinear motion, okay? Rotation about a fixed axis, okay? So then in this case, any point inside the body will be having a circular motion, okay? You'll have a circular path, okay? In general motion, then it's kind of combination of both translation and rotational motion, okay, together. Let's take a look on an example here, okay? So if this is part of machine here, okay? So you can see if this is rotating, then this cylinder or this piston here, and it's going to be going back and forth, okay? So for the piston here, it will just have rectilinear translational motion, okay? But for this guy, the wheel here, and then this crank over here, this crank, this part of it is rotating about this axis here. So this and this will have rotational motion, okay? Each about a fixed axis, all right? This guy here, so this guy here will have curvilinear translation, okay? So it's going to be going down this way and this way. Now, because this R and this R are the same, so then this point and this point, okay, if you look at this body, it will actually think about next moment, okay? It's going to be at this point, and then this end is going to be this point. So then this guy will have actually curvilinear translation, okay? If any 2 points you connect them, the line is going to be parallel to an instant later that line where it sits, okay, or where it is at. So, but the motion itself is kind of curved around, okay? So then it's curvilinear translation. Now this rod here actually will have combination of translational motion and then the rotational motion, okay? So it will have complicated motion on this rod here. So this figure here shows you examples of each of the motions we just talked about, okay? So in general, if you have a rigid body, let's say this shaded area over here, that's a rigid body, okay? So it might have rotational motion, okay? It might just have translational motion. So for example, if in this case, okay, so if this body is it's moving, it has certain motion here, so then we can always pick, if say this point over here, you can take that as a reference, okay? And then you can have a fixed coordinate system which is at a fixed point somewhere outside the body. Now you can also think about inside the body to be also a translating coordinate system. So then this coordinate system is actually moving, okay? But this point, A point, you might have the information about its movement in the fixed coordinate system, okay? So it's easy to do it that way. So this is then kind of relative motion. We are talking about the motion of any point B inside the body relative to point A, okay? Given that A's motion can be described with respect to the fixed coordinate system. So then if that's the case, then the motion of B can also be determined by using the relative motion relationship between point A and B, okay? So then in that case, position vector of B in the fixed coordinate system should be equal to the position vector of A in the fixed coordinate system plus this position vector B relative to A, or B in the coordinate of this translating coordinate system, okay? It's the relative motion here then. All right. So then for velocity, you simply doing time derivative, okay, of this equation. So time derivative of this one will give you velocity vector, okay, equals to time derivative of r vector will be velocity of A, and then plus time derivative of r B with respect to A, okay? So that's that guy. Now, if this body is having just translational motion, then R relative to B is not changing, okay? Because that's translational motion, what is it's defined, okay? Inside the body, they share the same velocity and everything, so then the relative position wouldn't change, okay? So then this guy will be 0, all right? So if that's the case, then simply VB is going to be the same as VA, okay? So also then you can see that the oscillation of point A and point B are the same, okay? So this is for translational motion of the rigid body, okay? That's the relationships you have, okay? All right. Now, if you have rotational motion, okay, so then if you have a fixed axis, okay, so any point inside the body will have a circular path, okay? So at any position, a particular position P here, okay, you can define, because this is not having angular or rotational motion here, so then you can define, you can pick a reference line. So in this case, you can pick a reference line over here. Then the position of P can be defined, the angular position of it can be defined with this angle theta, okay? So, and then the change in the angular position will be d theta, okay? It's called angular displacement. The angle theta could be in revolutions, could be in radians, okay, and then could be in degrees, okay. So you guys should know already by now what will be the conversion factors between each two of the units here, okay. So one revolution should be equal to 2 pi radians, and then one revolution is equal to 360 degrees. 2 pi is equal to 360 degrees, okay. So if we define that angular position theta, then angular velocity can be defined similarly to what we had for linear motion. So you will be doing derivative of the angular position with dt, will give you the angular velocity omega, okay? So typically we take counterclockwise to be positive for the angle. So then omega would also have the positive direction in the counterclockwise direction, okay? And then clockwise would be negative, okay? Similarly for oscillation, all right? So oscillation will be, angular oscillation will be twice time derivative, okay, of the second time derivative of the angular position, okay? So all the time derivative of the angular velocity, all right? And then you should remember this relationship from linear motion where A acceleration is equal to V dV over ds. Okay, similar. So this will be similar. Okay, it's basically from the definition of this guy and that guy, you will arrive at this relationship. Okay, so this is when you have a rigid body that is having rotational motion. So then we'll use the angle as angular displacement, and then we will start from there. Okay. If the acceleration is being constant, then we would have this very similar equations as we had in linear motion when the acceleration is equal to constant. Okay, so in this case, we are talking about rotational. So then we are talking about angular acceleration being constant. Okay, so then you have this final velocity, angular velocity equal to initial angular velocity plus the angular acceleration, the constant angular acceleration. So alpha sub c times t. Okay, and then also this equation and that equation. Okay, so you guys should be familiar with these equations by now. All right. So for the magnitude of the velocity, okay, so it's going to be I think we learned this in circular motion, so it's similar. Okay, so rotational. So each point is having a circular path. So then all the equations in the circular motion will apply here for each other point. Okay, so the magnitude will be omega times r. Okay, and this is the magnitude. And then for the direction, okay, it's going to be in the tangential direction. Okay, here f is rotating in this direction. Okay. So in order to determine the direction here, we can also have the direction determined from the vector multiplication or cross product of the vectors. Okay, so for velocity, linear velocity vector v should be equal to the omega angular velocity times rp. Okay, so omega will have a direction that is counterclockwise as positive. Okay, so then in order to implement that, we are going to use right hand rule here. So if your four fingers curve around with the direction of the omega, okay, the rotational motion, then your thumb is going to be pointing in the direction, the vector direction of omega. Okay, so this only gives you the kind of convention for the direction of omega. Okay, so to be the positive upward in this case. Okay, so in this case, let me switch my camera over here so you can see how this being constructed. So on the figure here, the omega goes in this direction, all right, the counterclockwise direction. Then your thumb will indicate the vector direction of omega. Okay, so if you treat omega as a vector, then this is the direction of omega. Okay, omega is pointing upward. All right, now rp is in that direction over there. Okay, if you check on the figure over here, it's in that direction over here. So then v will be defined as omega as a vector cross product of rp. Okay, and then if rp is equal to r, then it's omega cross r. Okay, so then the direction of v will be determined. It's going to be in that direction using the rules for cross product of vector omega and then vector p. Okay, so it's called right hand rule, which is in this equation here. Okay, in this slice here. So the right hand rule says if you use your right hand, okay, so take out your right hand. Okay, now your index finger, okay, it's the direction of the first vector. Okay, it's a vector, and then your middle finger is the direction of the second vector. If you are doing first vector cross second vector, in this case a cross b. Okay, then put this up in this way, then the thumb will be in the direction of the cross product of the two vectors a cross b. Okay, so in the case we have omega cross r. So omega was in the previous slides was in the upward direction, right? And then r is pointing in that direction. So then your thumb is pointing in that direction. So that's how the V will be determined. Okay, so you can use this right hand rule. Okay, I think there's different kind versions of right hand rules. You guys can pick. There's a couple of them, but take the one you are most familiar with. Okay, to determine the direction of the cross product of two vectors. Okay, all right. Um, so that's what we have for the velocity, linear velocity. Now let's take a look on the oscillation. Okay, so again, since the any point in the rigid body will have a circular path, so then whatever we learn in the circular motion for a point object will apply here. So at any particular point P, the oscillation at that point is going to have two components, one in normal direction, one in the tangential direction. Okay, so AM and A sub T, A sub N and A sub T as the two components for the oscillation. Okay, and then in the scalar form, we learned that in tangential direction, it should be alpha times R. In the normal direction, it should be omega squared times R. Okay, so that's the scalar form. We can get the magnitude. Okay. So the tangential direction of the oscillation AT, it tells you how fast the rate of change of velocity will be. Okay, so that tells you if it's non-zero, that tells you velocity, the magnitude is changing. Okay, and then AN will change the direction of the velocity. Okay, so in that fashion. All right. Now, since velocity is defined as omega cross p in the vector form, so then oscillation, if you look at in the vector formula or in vector form, we can see that vector, because it's defined as time derivative of velocity. Okay, now velocity is the cross product of these two, so then you'll do this chain rule here for the derivation. Okay, so you'll be doing derivative to the first term and cross the second term plus the first term again cross the derivative of the second term. Okay, so in this case, you can see if you're doing d omega dt, that will give you oscillation, angular oscillation. Okay, and then if you are doing dr over dt, okay, that's going to be the v, the velocity, which is defined as omega cross rp. Okay, so because this gives you velocity, then it's going to be in that term. Okay, so and in this case, again, it clearly shows you that oscillation will have two components. This component, okay, you can use again right-hand rule to determine what will be the direction of this component. Okay, and then you can also check at what's the direction of this term over here. Now you will have to apply right-hand rule twice. Okay, so the first time in here in the parentheses, you're determining the velocity, the direction of the velocity, and then you are doing omega cross velocity. That will give you the direction. But this will be the tangential direction. The first term will be the tangential direction. The second term will be in the normal direction. Okay, after you have done that. Okay, again, for the vector form of alpha angular oscillation, we will take again the same direction as the omega. Okay, so it will be the upward. Okay, to be the direction of the alpha. Okay, so again, if this is the rotational axis, then you are going to curl your forefingers with the direction of rotation. The thumb will be in the direction of the angular velocity omega, and then also angular oscillation omega alpha. Okay, omega and alpha will be in the same direction, just in this case. Okay, when you have rotation. All right. All right. So at the end, you can also now on this one here, you can look at the magnitude and the directions. Okay, so for the magnitude, this will turn out that the direction is going to be this guy. Okay, omega squared times r. Or if you are doing cross product here, you'll see that. Okay, then it's going to be minus omega squared r. Okay, so A cross R will be the A tangential, and then normal direction, A normal direction will be equal to minus omega squared times R, okay? So then the magnitude of the overall acceleration vector should be the normal direction square plus the tangential direction square, then take square root of it, okay? All right. The procedures for solving a problem with rotational about a fixed axis, okay, so you want to take sign convention for the axis rotation, okay, so again, typically we say if this guy is rotating in the counterclockwise, that's positive, okay, otherwise it's negative, okay, and then the sign convention or the direction convention for the angular velocity and acceleration velocity will be you use your right hand, curl your four fingers in the direction of rotation, and then the thumb will be in the direction of the omega and the acceleration alpha, okay? All right. So if the relationship is known between any two of the variables, okay, then the other variables can be determined, okay, from these three formulas or three differential equations here, okay? So from the definition, omega equal to d theta over dt, and alpha equal to d omega dt, and then also alpha times d theta should be equal to omega d omega, okay? If alpha is constant, then you will use the equation for constant angular oscillation, the three equations a couple of slides back, okay? To determine the motion of a point, the scalar equation V equal to omega R, AT equal to alpha R, AN equal to omega square R, and then the A equal to like two components square, and then take square root of the sum can be applied, okay? So you can use those. Now, another way to determine the vector form of the equations, okay, you can also use the IJK components, okay? So then you'll be following the rules for vector cross product, okay? So if you haven't learned the rules for vector cross product, you can probably Google it online and it will tell you the procedure, okay? So basically, that's the one we mentioned last time on the calculating the determinant of the 3x3 matrix, okay? So the two vectors, if you use the IJK components, then you pretty much have you can set up the 3x3 matrix and you can calculate the determinant of it, okay? All right. Let's take a look on this concept quiz here. Let's do it one by one, okay? There's a feature that called breakout rooms I haven't tried, so let me see if we can try that, okay? So how do I do that? Breakout rooms, let me see. So we have 10 people here. Let's do a breakout rooms of 4. Okay. So then I'll divide you guys into a group of 2 or 3. Okay. So and then you can talk. You can kind of have discussion on how do you want to solve the problems. Okay. So we can have some conversation here. So create breakout rooms. Okay. It's randomly selected. Okay. So I have room 1 with Casey, Parker, and Seth. I have room 2, Macy, Maria, Marcus, and then Andrew and Morgan will be in room 3. Nasanet and Obi will be in room 4. Okay, so you guys can have conversations over there.
Oh, you're recording?
Hi, I'm just checking in.
Oh, hello. I was reading the question. So our angular acceleration is constant, so we can use those equations to find B.
Yes, sir.
Okay. So our disk is rotating at 4 rads per second, and our acceleration is 2. So we can use the Oh, are you recording now?
I guess you're working on the
Oh, you are.
comments.
Yeah, we can't figure out one, but we thought that two was D. Is that correct?
Okay. Yeah, D is correct. Yes, 2 is D.
Yeah.
Okay. So yeah, let's leave the room. Let's go back to the main room. We can
Okay.
talk about that there. Okay.
How do you leave?
So if you click on the breakout rooms at the bottom here, then you will have option to leave it.
All right, so he's back now. There he is.
We were worried about you.
Oh, he's muted.
Yeah, we can't hear you.
All right. Yeah, I went to check OBM NestNet in their breakout rooms. So we are back, I think.
I'm back.
Yeah, everyone is back. Okay, let's see. So let's go back here. So this one says a disk is rotating at 4 radians per second if it's subject to a constant angular oscillation of 2 radians per second squared. Determine the oscillation at point B. Okay, so if we go back to the previous slide, let me see here on the oscillation. Okay, so the oscillation. Pull this up. Switch my camera. Okay, so we would have oscillation equal to alpha cross R minus omega square R. Okay, so that's the equation you want to apply on this oscillation here. Okay, so it says rotating at 4. This is clockwise. Okay, so then the oscillation at this point B here. All right, you'll be looking at the tangential component, which is this guy, okay? And then the normal direction will be this guy, okay? So in this case, if you look at this one here, all right, this is easy because this one is just a vector r, okay? So vector r at point B is pointing in the negative j, okay? R is in the negative r times j direction. This is the magnitude, okay? This is the direction with negative there. So then omega square will be, it's a scalar, so it will be the 4 square, so that gives you 16 times. The r here is, I believe, is 2, okay? So minus 2 in the j direction, and then with the negative sign. So in minus will get you 32j, okay? So we have determined the j component to be positive j. So then looking at that, you can eliminate b and d, okay? So then we'll be looking at now the I direction will be in this case, okay? So in this case, if you use your right hand rule, okay, so let's see, alpha here is going to be 2, okay, I is 2, so the magnitude will be 4, but the question is now would it be positive or negative here, okay? So you're going to use your right hand rule. In the situation, this is going to be, your forefinger is going to be in that direction, okay? So then your omega in this case will be, or your alpha in this case will be pointing into the screen, okay? Because you're going to curve your forefingers in the direction of omega, then that's going to be your alpha direction, okay? So alpha cross R, alpha is going into the paper, okay, if we use a dot. R is in this direction, okay? So then you're going to use your right hand rule. Again, it's going to be in that direction and then this, okay? I don't know if you can see this clearly, but the index finger goes into the paper, the middle finger goes in the direction of R, which is pointing downward, okay? So that the thumb will be in the direction of the right, left, okay? So left means minus, okay? So then in the case it will be C, okay? So C, the first one, that will be C, okay? It's going to be in the negative direction for the I, okay? So go that way, goes that way. All right. Any questions you guys have on that one? Is it clear?
How do you find R?
R at point B, right? It's at point B, so then B is over here. It's so you are connecting from the origin to point B, that's your R, right? R, it's negative J. It's given in the figure that R is equal to 2 feet. So the 2 feet is given in the figure, but the direction you can determine from the figure there. Okay. That's the X, next Y, and then this is B over here. Okay, so this is R for B. So it's going, this is Y, this is X. So this is going to be minus J. Okay.
I didn't see the 2 feet there.
On the figure, you didn't see it?
No, I didn't notice it.
Okay, you didn't notice. Okay, that's fine. But yeah, it was there. Okay, so yeah, sometimes the informations are given in the figure. Okay, so as well. So we want to look carefully on both the figure and the problem. Okay, I think the textbook of this one does that kind of consistently from the beginning to the end. So a lot of times you'll look at the figure that has a lot of more information on the figure. Okay, and then the problem in the statement, it only have a very short statement. So then you want to find additional information in the figure. Okay. All right, so this is the first one. First one is kind of complicated. Okay, it's more complicated than second one. Second one is kind of straightforward. Okay, second one, it says if a frisbee is thrown and curves to the right, okay, so it's experiencing, should be D, right? General plane motion, because it's having translational motion as well as rotational motion. Okay, so the combination of the two. So then second one will be D. Okay, so we can actually get the second one straight out of that. Okay. All right. Close this up there. Okay, so let's take a look on the attention quiz here. I don't think we'll have time for the breakout room here, but let's take a look at this two together, okay? So the first one here says you have a fan blades suddenly experience an angular oscillation of 2 radians per second, okay? If the blades are rotating with an initial angular velocity of 4, determine the speed at point P where the blades have turned 2 revolutions, okay? Now, this one gives you, let me see, this one gives you the oscillation, angular oscillation alpha, okay? It gives you initial omega, so omega 0 is known. It says determine the speed at point P where it has turned 2 revolutions, okay? So, so in order to figure out speed V, because V is defined as omega cross R, okay? At point P, then RP or R. So whatever, because R is going to be 1.75, this notation, okay? But you are looking for the speed, that means you are just looking for the magnitude, okay? So then you're just looking for omega times R, okay, at that point. R is given as 1.75, you just need to figure out what's omega, okay? Omega is going to be equal to, in this case, it tells you the oscillation as constant 2 radians per second. So you can apply this equation. Omega final, this is final equal to initial plus, or actually, no, we're using this one here. Final square equal to initial square plus 2 times alpha times theta minus theta 0, okay? This is equal to 2 pi in radians, or 2 revolutions, okay? So then you can solve for this one, okay, because this one is given as initial 4. this is 2, okay? So omega is going to be equal to omega square equal to this guy, this 4 square plus 2 times 2 times 2 pi, okay? And then you'll take square root to solve for omega, okay? This turned out to be 8.14 radians per second. It's already, I think it's given in the problem, but we can manage how to solve for this, okay? So once this is given, then you'll be doing just plugging the number here, 8.14 multiplied by that guy, that will give you 14.2 feet per second, okay? So that would be answer A. For somehow I wrote down answer B, but it should be A, okay? So that's on that one, the first one there. Okay. For the second one here, it says determine the magnitude of oscillation at point P when the blade have turned 2 revolution. Okay, the same thing here, all right? But now we will be looking at, because oscillation should be equal to alpha cross R minus omega square R, okay? So there's 2 components, AT here, this is AT normal component, tangential component, this is normal component, okay? So you're looking for magnitude again, so then you'll be looking at A equal to square root of AT square plus AN square, okay? So you need to figure out AT and AN, okay? AT, the magnitude, we are just going to be using alpha times R, the scalar formula, okay? So alpha is equal to 2, and then R is 1.75, so that should be 3.5, okay? AN will be minus omega square times R, okay? Or if you are just looking at the magnitude, then it doesn't matter, the negative sign wouldn't count anyway, but we can keep it. Square omega is 8.14, R is 1.75, so that would be 115.95, okay? So then take this numbers in there, take this number in there. Whether you have a negative sign or not doesn't really matter, because you are going to square it, okay? So 3.5 square plus 115.95 square, okay? That will tell you this is going to be equal to 116 feet per second square, okay, on this one here. So then the answer will be D on the second, okay? The first one should be A, and the second one should be D. All right. You guys have questions on this one? If not, then let's quickly take a look on the example here, and then I'm going to just post the solutions for the groups of problem solving later, okay, after the class. So this one says if you have 2 motors A and B, with A has constant angular oscillation alpha A 4.5 radians per second square, starting from rest, the cord is wrapped around pulley D, which is rigidly attached to gear B, okay? Find the velocity of the cylinder C and the distance it traveled in 3 seconds, okay? So the plan to tackle this problem is been listed here. So you want to relate the oscillation of B to gear A, because alpha A is given. So then you can figure out alpha B first, okay? Once you have alpha B, then for the D, the disc D, pulley D should share the same alpha as B, okay, the gear D, B. So then once you have that, you can solve for the problem. You can calculate the velocity at point C, and then also the distance traveled. So the velocity at point C should be the same as point P, okay, or P prime there, listed there, okay? So we'll take a look at the solution here quickly. So when the 2 gears have different radius, at the point of contact, they should share the same oscillation, okay, because that's the common point. So it will share the common point here, the two gear will show the same velocity and oscillation, okay. So you are given oscillation, so you are going to use this shared oscillation at that point P. So alpha A, RA is going to be alpha B, RB, okay. So then you can solve for alpha B, the angular oscillation for B to be 1.5, all right. Then D and B, because they are welded together, so D will have the same angular oscillation as B, okay. So 1.5 as that one, all right. So then after that, okay, so you can solve for the oscillation at point C by using alpha, the relationship between angular oscillation and the radius, okay. So at point C should be alpha D times RD, okay. So that's the oscillation of the point C. Once you have oscillation, you can figure out the velocity and then distance travel, okay, because this is a constant oscillation problem there, okay. So you can do it that way. So use those two equations to solve for that, all right. Any questions you guys might have on this one? If not, then it's time to have you guys dismissed for the class, okay? So I will post solution for the group problem solving later, all right? So that will be it for today then. See you guys. Bye.
See ya.
See you.
Bye.
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 Bye again.